Let's continue our investigation into the quantum LC circuit. In the previous video, which was part 1, I defined the ladder operators. I'm going to write down the ladder operators again. A with a hat is equal to the square root of 1 over 2 h bar z. This z is the impedance. And then we're multiplying by phi with a hat, it's an operator, plus I z times q. And q is the charge, phi is the flux. So these guys are both operators in quantum mechanics. So that's A, but we also have A dagger, which is the Hermitian adjoint. So let's write down A dagger. A dagger has the same coefficient out the front, the square root of 1 over 2 h bar z. And all we have to do is change this plus sign to a minus sign. So we have phi hat minus I z q. So these collectively are known as the ladder operators. They're sometimes also called the raising and lowering or the creation and annihilation operators. But I'm just going to call them the ladder operators A and A dagger. In the previous video, I also derived expressions for phi and q in terms of the ladder operators. So let's write down phi first. Phi is equal to the square root of h bar z on 2. And then we have the sum of A dagger and A. And there's a similar expression for q as well. Q is equal to I times the square root of h bar on 2z times the difference of these ladder operators. So that's the important difference between these two expressions. Over here we have a plus sign, over here we have a minus sign. Another important difference is that we have an I over here. And this imaginary unit ensures that this is a Hermitian operator. If we take the Hermitian adjoint of this A dagger turns to A, and this A turns to A dagger. So we're just swapping these guys around. And addition of these operators is commutative, so we have the same thing. But over here, when we take the Hermitian adjoint, this A dagger gets swapped to an A, and this A gets swapped to an A dagger. So we actually swap these guys around, and we have a minus sign. But that minus sign is counteracted by this I, which also gets negated. Because when we take the Hermitian adjoint, I goes to minus I. So those two minus signs cancel each other out when we take the Hermitian conjugate. So we get back to where we started. So both of these guys are Hermitian operators. They correspond to physical observables. They are measurable quantities. So these are the definitions that we had in the previous video, in part 1. Now, for part 2, what I want to do is write the Hamiltonian in this form. So this is capital H, the Hamiltonian. I'm going to write it as h bar omega over 2 times A dagger A plus A dagger. These two terms are not the same. A dagger A and A dagger are not equal to each other. It's because these guys do not commute. In fact, their commutator is equal to 1. So it's not equal to 0. If it was equal to 0, then they would be commuting operators. But it's not equal to 0, it's equal to 1. That's another commutation relation that we wrote down in part 1. Now what I want to do is I want to substitute these definitions into this form of the Hamiltonian. And that's actually what I'm going to use to recover the original form of the Hamiltonian that we translated from classical mechanics. So let's go ahead and do that. First, we're going to have this h bar omega over 2. Then, what is going to be present out the front? Well, when we multiply these two guys together, we're going to multiply this square root coefficient by this square root coefficient. And when we square this, because we're multiplying by the same thing, the square root sign is going to disappear. So we're just going to have 1 on 2 h bar z. So that's 1 on 2 h bar z. And that term is going to be present in both of these terms. So there's going to be a coefficient in both of these guys. And we can just pull that coefficient out the front. So that's what we have over here. Now, what else is there going to be? So for A dagger A, we're going to have this combination times this combination. So we will have phi minus IZQ times phi plus IZQ. And then we're going to add to that the reverse of this. So we're going to have phi plus IZQ, and then phi minus IZQ. A lot of very similar terms, but the order is very important. These are not commuting operators. So this is all the stuff that we have over here. So this is equivalent to this form of the Hamiltonian. I've just substituted these definitions into this expression. So we've got all of those constants taken out the front. Those coefficients are over here. And what's going on over here? This is a minus, then plus, then plus, then minus. So when we have minus plus, plus minus, that corresponds to A dagger A, and then we have A dagger. That is the ordering that we see in this definition. Now let's expand all of this out in the line below. First, let's group these coefficients together. So what are we going to get? H bar cancels with H bar. 2 times 2 is 4. So we have omega on 4z. And z is the impedance. So what is going to happen when we expand all of these guys out? Let's see what we get. First, if we take this phi and this phi, we're going to get phi squared. We're also going to get phi times phi over here. So we're going to have 2 phi squared. So that's 2 phi squared. Now let's take a look at this term and this term. Here we have minus I and plus I. Minus I and plus I are multiplicative inverses of each other, so we're going to get plus 1 from that. And a similar thing is going to happen over here, because we have plus I and minus I. The order of these complex numbers does not matter. These are not operators, they are just numbers. So if we multiply those guys together, we're just going to get plus 1. Then we're going to have 2 factors of z. We're going to have z squared over here and z squared over here. And we're also going to have those q's. We have q times q and q times q. So that's going to give us plus 2 times z squared q squared. So it's a factor of 2 over here because we have 1 copy from this combination and 1 copy from this combination. All of those i's disappear because we have an I times a minus I. And that just gives a plus 1. So those 2 terms are very important. Now let's have a look at all of the cross terms. So what we've done is we've just looked at phi's with phi's and q's with q's. But now let's have a look at some mixed terms in between where we have a phi and a q and a q and a phi. So first, let's focus on this part over here. We can factor out I, z, and we can see that we have a phi and then a q. And then we can swap the order around, and then we get a q and a phi with a minus sign. That's a q and a phi. And it's important to remember that the minus sign occurs over here. We have minus q and then phi. So q and phi, they have the minus sign, but these guys do not have the minus sign. And we can identify this combination as the commutator of phi with q. And this is actually a canonical commutation relation. It's just like position and momentum. This is equal to IH bar. The commutator of position and momentum is IH bar, and over here the analogous quantities are flux and charge. So the commutator in quantum mechanics of flux and charge is also IH bar times the identity operator. But the identity operator is usually implied, and it's not explicitly written all the time. So that's what we have over here. But I'm not going to evaluate it because if we look over here, we're also going to have a very similar term. I'm going to factor out a minus IZ, and then if I take this term and this term, I have a minus sign, which I factored out. So that's phi q. And over here I have q phi with a plus sign. But if I take out a minus sign, I have to have another minus sign. And that's going to give me this, minus q phi. So here I have phi q, and then minus q phi. So this plus sign gets turned into a minus because we have another minus sign here. Minus times minus gives us a plus. And this is the exact same combination that we have over here. There's a plus sign and a minus sign, so these guys are going to cancel. So we don't actually even have to worry about the canonical commutation relation. It's because these guys are going to cancel. And that's because I wrote the Hamiltonian in this form. So now we can cancel these guys out. Let me just close the bracket. We can cancel these two terms out. And the only terms that are going to remain are these terms over here. So let me move some of these coefficients to the inside, and let me factor that 2 outside. And I'm also going to switch the order. I'm going to put q squared first. So I'm going to have 1/2 of, what is going to be multiplying q squared? Well, if I bring in this 1 over z, that's going to cancel with one of these z's and the z squared. So I'm going to have omega times z. So we have omega times z, and we're going to times that by q squared. So that is this term over here, omega times z, and we have a q squared. And when I factor this 2 out over here, I get 2 on 4, which is 1/2. Now let's focus on this phi squared. This phi squared is just going to have omega on z. So we're going to have omega over z times phi squared. So you can see that we have the reciprocal of the impedance over here. Now I'm going to write both omega and z in terms of L and C. So then we're going to see a very important relationship. And I forgot to write a 2 over here. This is a squared. So we have q squared and phi squared. That's come from these two terms. And these two terms that can be identified as the commutators have both cancelled out. Now, let's write this out in full. We're going to have 1/2 times, let's have a look at it over here. Omega is 1 over the square root of LC. And this z is the same as the square root of L on C. Then q squared is going to be over here. So we have this q squared. Now let's have a look at this term over here. We have, again, 1 over the square root of LC. That's that omega. And then we have to take the reciprocal of the impedance. And the reciprocal of the impedance is the square root of C over L. That's just the reciprocal of what we have over here. And then we have phi squared. So that's phi squared. I'll close the bracket. So let's see some simplifications that can be made. Here we have an L inside the square root and an L inside the square root over here. There's an L in the top and in the bottom, so those guys are going to cancel. A similar thing is going to happen with the C over here. C is in the top and C is in the bottom. Over here we have the square root of C squared, which is just C. So we're just dividing by C over here. And over here we have 1 over the square root of L squared. So we have L squared over here, and we're taking the square root. That's just going to leave L. So we're just going to be dividing by L and dividing by C. And then we can bring that factor of 1/2 in, and we can write this as q squared over 2c plus phi squared over 2L. And that is exactly the Hamiltonian that we found in classical mechanics. And then all we did is we changed q and phi to operators, and we added a little hat on top, and that is how we got this Hamiltonian. So in part 1, in the previous video, we started with this Hamiltonian, and then we substituted in these definitions to get this expression, and now we've done the reverse. We've started with this form of the Hamiltonian in terms of the ladder operators, and we've substituted these definitions, and that's got us back to where we started. So we've done a lot of interesting algebra to get to this point. So just remember that this square root of L and C is the impedance, and omega, that angular frequency of oscillation, is 1 over the square root of LC. Now, the next thing I want to do is write this in a slightly different form. I'm going to define some new variables that are actually dimensionless quantities. So let me label H, Q, H, O for quantum harmonic oscillator, because this LC circuit is actually a quantum harmonic oscillator. Let me label that in the following way. So this is the notation I'm going to use. I'm going to write this exact same Hamiltonian, but with some extra factors. I'm going to write 2e squared over 2c. I'm going to multiply that by this operator q over 2e all squared. And then I'm going to add to that 1/2. So we have a plus sign. This is a plus sign over here. And this is 1/2. And we need a new constant, which I'm going to label as phi naught. This is a constant. This is not an operator. I'm going to divide this by 2 pi. Then I'm going to square it and divide it by L. This L is the inductance. And then, in brackets, I'm going to write 2 pi times this operator phi with a hat divided by phi naught. So this phi naught, or phi sub 0, that is a constant. This is not an operator. This is just a number. But this is the operator phi. It's got a hat on top. And let me close this bracket and square this. So let's see what we have over here. We essentially have the exact same equation. We have the same expression for the Hamiltonian. What I've done in this term is I've multiplied and divided by 2e all squared. This 2e squared and this 2e squared, they get cancelled. So this is exactly the same as this term. What about this term over here? This 1/2 is still there, and this 1 over L is still there. But what I've done is I've multiplied by this factor, phi naught over 2 pi all squared. And then I've divided by that factor over here. So you can see that this factor over here and this factor, they can be cancelled out, and we get back to what we started with. Now I'm going to relabel some of these guys in different ways. Let me call, I'll use green for this. Let me call this guy over here E sub C. So the energy associated with the capacitance. And let me call this lowercase n with a hat. So this is the lowercase n with a hat. This is a new type of operator. It's a dimensionless operator. And let me call all of this over here, I'll call this E sub L. And this L stands for the inductance. And all of this stuff inside the brackets over here, I'm going to relabel as lowercase phi. So this is, again, a dimensionless quantity. We can call this the phase. And now what we can do is we can write this Hamiltonian in the following way. We can write this as EC times n hat squared plus EL times this lowercase phi squared over 2. So can you see what I just did here? I've just multiplied and divided by some fundamental constants like phi and the charge of the electron, and that's given me all of this stuff over here. So I've just rearranged and combined all of these little factors out the front into these terms. We have some freedom when we're defining this and this over here. We could absorb this factor of 1/2 inside this definition. And for this definition of EC, we could also move this factor of 4 out. Because we have 2 squared over here, we could move that 4 outside, and then we could write 4 EC over here. So we have freedom when we're defining these parameters over here. But for this video, I'm going to use this definition. I've just grouped these guys together in the following way. So this is exactly the same Hamiltonian, but it's just written in terms of dimensionless quantities. These guys don't have any units. And that allows us to have a much more convenient way of describing this system that doesn't actually depend on the physical value of these quantities. It just depends on a dimensionless parameter. So one thing that I want to define as well is this phi sub 0. So phi sub 0, or phi naught, is actually equal to Planck's constant over 2e. And E is the charge of the electron, or it's the absolute value of the charge of the electron. So H is Planck's constant, and this is the charge of the electron. That is condensed into this notation where we have phi naught. So that's the phi naught that appears over here and over here. So this is the Hamiltonian for the quantum harmonic oscillator that is associated with the LC circuit. So we have quantized the LC circuit. Now let's have a look at some very important relationships. So let me write down some very important relationships. We can use similar reasoning to what we have up in the top right, and we can define this phi, so this phi hat, as some constant, phi ZPF, and ZPF stands for 0-point fluctuations, and this constant is going to multiply A dagger plus A. And this term over here, this expression, is analogous to what we have up here. So you can see you have a coefficient out the front, which I've just called phi ZPF, and then we have the sum of the ladder operators. So all we've done is changed the coefficient out the front. Otherwise, this is the same operator. We just have a different coefficient multiplying it to get rid of its physical dimensions. We can also write down another analogous form that is going to tell us what this n is going to be. So n hat is equal to I times some coefficient, which I'll call n ZPF. Again, ZPF stands for 0-point fluctuations. And now what we're going to have is the difference of A dagger minus A. So that's the difference of these guys. So you can see that these two expressions are analogous to these two expressions. All we've done is changed this coefficient out the front to get rid of the units. So this is a dimensionless quantity and this is a dimensionless quantity. Why do we keep seeing 2 times the electron charge appearing in these definitions? We have 2e over here, 2e, and then we have 2e over here. That's because these types of physical systems are going to involve pairs of electrons. And those pairs of electrons are actually called Cooper pairs. And this is important when we're describing superconductors, because these are actually going to be superconducting circuits. So now what we're going to do is we're going to actually change this term over here and this term, and we're going to find that there are other types of elements, not just capacitors and inductors. But before I do that, I want to write down the fundamental commutation relation between these guys. So there is a fundamental commutation relation. It's phi and n. This fundamental commutation relation is actually just equal to I. There is no h bar here. So if we had these guys together, we took the commutator of phi with q, we would get I times h bar. It's just like position and momentum. But that is not the case over here because these are dimensionless quantities. So there is no h bar over here. This h bar has disappeared. But we still have an I. These guys do not commute with each other. So this is the canonical commutation relation. Just remember that this is lowercase phi. We can call it the phase, or the superconducting phase. And this is a dimensionless quantity. It's a dimensionless operator that is associated with the charge. It tells us how many quanta of charge are there in this circuit. So now that we've written all of this stuff in these alternative dimensionless quantities, let me write down 2 other important Hamiltonians. So first, I'll write down the Hamiltonian for the transmon. So I'll write that as H sub transmon. And what is this transmon over here? Well, it's a type of superconducting device. And it has a very similar Hamiltonian to that Hamiltonian up here. So it also has a capacitor. So it has this term with an n squared. But it does not have a quadratic dependence on phi. It actually has a nonlinear dependence. It has minus some coefficient, which I'll call E sub j, times cosine of phi. So we have the cosine of phi over here. And this j stands for Josephson junction. Because we no longer have an inductor for this Hamiltonian, we have a Josephson junction. Let me write down another Hamiltonian. I'll write it down over here. And this Hamiltonian is going to be the Hamiltonian of the Dualmon. So I'll write this out, Dualmon. And it's also a similar Hamiltonian, but instead of 2 quadratic dependences over here, we have 2 nonlinear dependences. Both are cosine. So we have minus E sub q, and I'll go into what this denotes in a second, times the cosine of 2 pi n minus Ej times the cosine of phi. So have a look at what we've done over here. We've turned these quadratic dependences into this cosine over here. And there's also a minus sign out the front. So this EQ is referring to a QPS, a quantum phase slip. This is another type of device. So this device is actually analogous to the capacitor. So the capacitor has turned into this QPS, and the inductor has turned into a Josephson junction. That's what this J stands for. So these are just different types of devices, and they have excellent properties. They have these very interesting nonlinear dependences over here. So this is the Hamiltonian for the Dualmon, and this is the Hamiltonian for the transmon. These Hamiltonians have applications in quantum computing. These are physical systems. They are superconducting circuits that have very important applications when we're actually trying to make physical qubits. So let me write down an important approximation at the bottom over here. Cosine of this phi over here can actually be approximated as 1 minus phi squared on 2 plus phi to the power of 4 over 4 factorial, which is 24, plus higher order terms. So you can have as many terms as you want, and that's going to give you more precision. Now have a look at this Taylor series approximation. We've seen this before. There's another video in the quantum mechanics playlist where I use Lagrangian and Hamiltonian mechanics to describe the pendulum. And the pendulum also had a Hamiltonian that had a very similar form to this. But keep in mind, this is just an analogy. This is not exactly the same as the pendulum, because we're dealing with operators over here. So this minus cosine in the potential energy term, this is analogous to the potential energy term, this is very similar to what we had for the pendulum. And we used the harmonic oscillator to approximate the pendulum with this Taylor series. That's because if we substitute this Taylor series in here, it's going to give us a constant term, which doesn't actually make much of a physical significance, because we're just going to be taking derivatives of the Hamiltonian. And then we get this quadratic term and this quartic term. This quadratic term has a minus sign, so we take minus times minus, that's going to give us a plus. That is exactly what we see over here with the inductor. So that tells us that the LC circuit, the quantum harmonic oscillator, is a very good starting point for finding an approximate solution to this type of system, the system of a transmon. So the transmon and the dualmon are very realistic systems. These are actual systems that you can build and make qubits out of. Why are these good candidates for making qubits in quantum computing? And why is this not a good candidate? Well, quantum harmonic oscillators have evenly spaced energy levels. But these guys do not have evenly spaced energy levels. They are anharmonic oscillators. The spacing between energy levels differs a little bit. And it's that property, the anharmonic oscillator property, that allows us to make qubits, or two-state systems, where we can just use the ground state and the first excited state. That is what a qubit is. And that is a very important thing when we're trying to build a qubit, a scalable qubit. And this has very important applications in quantum computing and actually building practical quantum computers. We're going to continue our discussion of these types of Hamiltonians in later videos in the quantum mechanics playlist. You can find those videos if you click over here.